right, thank you. So I'm going to tell you about some work that Mark, Wyatt and I have just finished up. I turned up on Astro PH last week at that number. Right, and so I'm going to try and summarise what we did for the next 15 minutes. So what is an exozody to start off with? So you should be thinking of a warm terrestrial zone debris. So this is something that's optically thin, it's only dust, no gas, or very little gas, collisions, things like that. So I'm going to first tell you about exozody and why they matter, and then I'm going to tell you about the brightness distribution that I've derived using data from the WISE mission, and they're going to show you a simple evolution model and some of the predictions that come from that. So here's one of the best examples we have of an exozody, a warm terrestrial zone debris disk in the HD 69830 system. What we have is 3 low-mass planets and a ring of dust at about 1 AU. And so this is a 3 billion-year-old star, sun-like star. So what we actually see is this photometry here. So the black dots are the photometry, the blue line is a stellar photosphere model. And so what you see in the mid-infrared is an excess which comes from the dust in this ring. And so what you see if you subtract the stellar photosphere from the photometry, and also for a simple black body model as I have here, then you're looking at dust that's about 300 Kelvin. And so it's infrared excesses like this that I'm looking for here. Okay, so we don't think that the warm dust in the HD 69830 system is simply a bright old asteroid belt, and the reason for that is shown in this plot. So this is showing the disk brightness as a function of time, which is the age of the star. And what these 4 lines are different initial masses for an asteroid belt. And so this is increasing in mass for each of these lines. So even if you put more mass into the asteroid belt, then it just decays more quickly. So by the time you get over to billion-year ages, you end up with the same brightness. And HD 69830 is up here. So this is a scenario that doesn't work. And this is a kind of model that I'm going to use later on, which decays as 1 over time. Right, so what do we think it could be? So one of the possibilities that I'm not actually going to consider here as I go further through my talk is comet delivery. So this is something that could be important in the solar system, where you have the Kuiper belt or a Kuiper belt sitting out at tens of AU, and then you can have planets inside there, and they will scatter some of these comets, and some of them will make it down into the terrestrial regions, and they will disrupt and leave material behind, which could give you a warm terrestrial zone debris disk, such as you might see in the HD 69830 system. Another possibility is you could have some kind of individual collision, so something between a planet and an asteroid, or an asteroid and another asteroid, or a comet, which could give you this kind of excess as well. Another possibility is a dynamical instability. So this could be a late heavy bombardment-like event where you have some planets that go unstable, and they will increase the random velocities of all the small bodies in the system, and they are more likely to collide. And some of that will happen in the terrestrial region, so that could also give you warm dust. And for my purposes here, I'm going to treat these as basically random in time throughout the main sequence lifetime of the stars that I'm considering. So now, if you're talking about young stars, so things not that much older than John has just talked about, you can have any of these scenarios, but you also have the possibility that you do have initially massive asteroid belts, because the star is not so old that they've decayed down to be undetectable. And another possibility is terrestrial planet formation. So if you're going to have Earth-Moon system forming events, and that's going to throw off some material and give you a warm excess at early times. And these are things that start at time equals 0. So for what I'm talking about today, the point is that exozody can hinder the detection of Earth-like planets around other stars. And the reason is just that if you have something like this, and then you have a planet sitting somewhere in here, then you just have an increased background. So it doesn't mean that you can't detect these planets, it just means that you need to integrate for longer. But if you're going to have some kind of time-limited space mission, then you're going to, it is going to make things more difficult. And so the point here is to try to characterize this distribution so that that can help with the planning of this kind of mission. And so this is an idea that I borrowed from Chris Stark, actually. Thank you, this slide. So this is just a way of splitting up some of the things that we might care about for exozodi. So on the left, I've talked about the structure. So in the solar system, you might have we have a structure like this. We have a resonant ring outside the Earth and a clump. So if you were trying to image an exo-Earth and you had a clump like this, you might confuse that with a planet. So that would be one kind of difficulty. It could also be the sign of a planet, so that's why I say problem. Now another possibility, you might have an Earth-Moon forming collision, and soon after you could have an asymmetric distribution that looks a bit like this. If you want to know more about that kind of idea, go and talk to Alan Jackson. Now you could also look at the brightness. So if you were to look at an individual system, you could be interested in whether the dust is more concentrated towards the inner regions or the outer regions or something like that. And most basically, the thing that you could look at is the luminosity function of the population. So how many stars have exozodi that are bright enough to make the detection of Earth-like planets difficult? Okay, so I'm not the first person to look at warm dust. This has been done basically ever since IRAS in the 80s. And all sky surveys have been really good for this because bright warm dust that you can detect with photometry is very rare. So you need to look at a lot of stars to find it. And so this has been, and if you're looking for terrestrial zone dust, then you want to be looking 10 to 20 microns. So things like Akari, IRAS, WISE, and MSX and Spitzer have also played a part. And so what all of this work has done is found a relatively small number of warm dust systems. And actually there's also a poster on work that's very similar to what I'm talking about here, so you can check that out as well. So what these surveys commonly don't do is talk about the number of stars that they've looked at, so the sample. So you don't necessarily know what the occurrence rates are for the objects that they're talking about. So my goal here is to put some lines on this plot. So I want to derive the 12 micron luminosity function, which is a cumulative plot. What is the fraction of stars with a disk to star flux ratio above some level at 12 microns? So this is similar to those mass plots that John was just showing, but it's in terms of flux ratio. So at the left side of this plot is about the solar system level, and about 10 to 20 times above that, for some assumptions, is the level at which your exozodi are going to make detection of exo-Earths difficult. And then above that, if it surveys 100 stars or so, LBTI, Large Binocular Telescope Interferometer, is going to probe this space. And there's a couple of posters on this that will tell you more about LBTI. The Keck interferometer NOAA has looked at a few dozen stars and set an upper limit here. Okay, so now moving into this grey box, this is where you can do stuff just with simple photometry. If you're down here, you need more specialised instruments. So this is where I'm going to be working. And in fact, last year I set a limit on the number of the fraction of stars that have bright exozodi using stars in the Kepler field. And there you're basically limited by the galactic background as well as confusion with extragalactic objects. So this is setting limits for the brightest skies down to very low levels. So what I'm going to tell you about now is I'm going to use WISE and stars that are observed with Hipparchus to get some detections down here and put a line here. But then to get down into this region where typical stars lie and where LBTI is going to be observing and where things matter for TPF, then I'm going to use a model to extrapolate down there. So just very quickly, the sample that I use is Hipparchus. I use a colour cut to get FGK-ish type stars and a line and an HR diagram to keep main sequence stars. And then from this sample of 24,000 stars, I use a W1 minus W3 colour cut, so that's using a 3 minus 12 micron colour to select about 100 candidates. And then from these 100, look through the images, made SCDs to try and figure out what was going on in each case to verify them, and actually threw out about 3/4 of them and ended up with 25 systems that look like they have real infrared excesses. And of those 25, 3 of them turn out to be protoplanetary disks that are not considered any further. And so if you're in the know with this kind of stuff, some of the well-known warm dust systems have been recovered, which is good. And the other thing that you notice is that there's a large fraction of these are in young moving groups. So this is SCO, CEN, Pleiades. And given that the Hipparchus stars are not on average young, if you pick out stars with infrared excesses, then it says that they are more likely to be young. So if I take those 22 stars and then put them on this plot and divide through by the number of stars in the sample, then you get one of the take-home points is that warm dust at the brightest levels is a 1 in 10,000 occurrence around nearby stars, and then going up to 1,000-ish by the time you get to the limits of what you can really do with WISE. But you can do better than that, because there is a tendency for these excesses to appear around young stars. So if I make an assumption that the ages in the sample are distributed evenly across the main sequence lifetime for each spectral type, then I get an age distribution, and then I can bin these 22 stars into a young sample, less than 120 million years, and an old sample, and then remake my plot with these numbers of stars in each bin. And then it turns out that the young stars have warm excesses at an occurrence rate of more like 1%, whereas the old stars are more like 1 in 10 to the 4. So for the evolution model, I've made a two-component model, which is motivated by those, by the data, but also by those scenarios that I told you about at the start. So all stars are born with an initially massive asteroid belt, and they also have some kind of random dust-forming event somewhere along the main sequence. So you have a picture of something like this. If this is brightness as a function of time, then you start out bright and then decay, and then at some point it becomes bright again and then decays again. And neither of these scenarios works individually. And so if I make some Monte Carlo realizations of this model, which is all of these grey lines, then there's reasonable agreement. And just to look at the age dependence again, I've plotted the two individual scenarios in two different age bins. So the black lines are a young age bin, 0 to 120 million years, and the blue lines are an old age bin, 5 to 13 billion years. So you can see that the initially massive asteroid belts dominate over the random collisions for young stars. But when you get to old stars, the random collisions dominate over the initially massive asteroid belts. And the reason for this is really reasonably simple, that the rare bright systems decay very rapidly, so it's very unlikely that you would catch them while they're really bright. So they spend most of their time decaying through fainter levels. So the existence of a few bright, rare guys up here implies a population of other guys down here. So now if I make the model for the entire sample, then I get this full plot. So this is the observations down here, and this is just one realization of the Monte Carlo model. So by the time you get down to typical stars, then you're actually talking about relatively high dust levels compared to the solar system. So the prediction from the simple model is good for LBTI, in that we expect a handful of detections over the next 5 years or so, but bad for TPF in that the typical levels are relatively bright. Okay, so the conclusions. Bright warm dust is a rare occurrence for old main sequence stars, and if you want to model these, then I need a two-component model to do it. And it could be that these random events actually dominate the dust level for old stars. So looking at old stars might not save you from the amount of dust. Now, of course, this prediction is model dependent, and LBTI will give us a strong test of this prediction, and then we'll be able to feed that back in and remodel once we have the results. Thanks. I don't know if that's right.
Any questions? Chris?
Thanks. You started your talk mentioning that there are several different mechanisms to generate the swarm dust. and it's not crazy to think that these different mechanisms would kick in at different ages. So is it valid to extrapolate from such high values down to such low values?
It's a model-dependent and uncertain prediction, and the reason I've chosen this model is because it's a simple one that I can actually do. So I don't believe that this model is the collisional model is necessarily any better than comet delivery, say. But to make a model for comet delivery, then you would need to know what the distribution of Kuiper belts and planets that scatter those Kuiper belts down to low levels are. And that could be time dependent, right? So, so I think you're right, and so this is a first go at it. Including the comet delivery stuff will be quite difficult because we don't. It's about the initial conditions. You don't know what the setup of the planetary systems are that could be delivering your material. So it's something that we'd like to do, but we don't necessarily have the information to be able to do it.
Steve?
So, Ron, thanks for
Wait for the mic.
Not sure. Yeah, okay. In the context of your model, you say you need these random collisions. Is it possible to estimate from your detection rate and so on how often these random collisions should appear in a system? Is it like once per lifetime around every star, or is it like 10, or not around every star it needs to be there? Do you have any idea?
Short answer, no, and the reason is, so in my model I say there is, it's not actually the main sequence lifetime because I have a range of spectral types. So it's once in 13 billion years, and there is a collisional time associated with this model that is actually the only free parameter. And so I could say instead of having one collision during that lifetime, I could have two, but I could just make them decay more rapidly. So I don't constrain it. However, the collisional time that I get for that I use is the same for both the initially massive asteroid belts and the random component, and that works if there is one collision during the main sequence lifetime. So I just use one for simplicity. So I couldn't say. I could speculate, but.
Stan Metcher, Stony Brook. Grant, thanks for mentioning the Patel poster. In fact, we did a similar survey of the WISE catalog with Hipparcos, doing W3 and W4, and we're finding, in fact, that 75% of the stars that show W3 excesses have stronger W4 excesses. So it doesn't seem like most of these are, in fact, exozodi. Do you have limits on W4 for the stars you're looking at?
So there are, I think there are W4 detections for most of them, and in most cases I can get a temperature, and that I have 2 excess points that I can throw a black body through, and there's a reasonable range of temperatures, but they're no colder than 100 Kelvin or something like that, maybe 150 Kelvin. So there's a range of temperatures, but none of these guys have 70 micron excesses, say. Even though the limits in a lot of cases are not very good, or 60 micron excesses from IRAS. So the temperatures that I got out of these are okay for warm dust, is what I would say. So they don't look like they're really cold guys, but they could be. They're not all sitting exactly at 1 AU. Thanks.
Okay, we got time for one more question, if anyone likes. No? Well, let's thank once again.